All right, let's just jump right into this explainer. Today, we're decoding the massive subterranean puzzle of earthquakes and tsunamis. If you've ever felt totally bogged down by all the heavy geological jargon, tectonic shifts, seismic waves, all that, well, you are exactly in the right place. We're going to take these insanely powerful, complex physical forces and break them down into crystal clear, highly retainable concepts that'll just stick in your brain.
So, here's our quick roadmap for today. First, the origin of earthquakes. Second, the race of seismic waves. Third, the mystery of shadow zones. Fourth, the measurement of earthquakes. And finally, plate tectonics and tsunamis. Let's get to it.
Starting off with Section 1, the origin of earthquakes. Let's talk about those subterranean forces.
We've got to begin way, way down deep beneath the crust. Down there, immense heat is basically turning tectonic plates into these incredibly stressed slow-motion bumper cars. They're just constantly colliding. Now, to really grasp how all that pent-up stress finally breaks loose, you just need to picture Professor Reed's elastic rebound theory. It's kind of like taking a thick plastic ruler and just bending it. As the plates jam together, solid miles of rock literally bend, building up massive tension. But eventually, that elastic limit is crossed, and when it is, snap. The rocks violently rebound back to their original shape. That huge, sudden release of trapped energy, that is your earthquake.
Now this actually clears up a massive exam trap and honestly a huge misconception in general. You hear news reports constantly talking about the epicenter, right? But the actual earthquake doesn't start there. Remember this trick, mol equals root. The focus, or hypocenter, is that deep, deep subterranean root where the rocks physically snap. The epicenter, on the other hand, is just the very first point on the surface to get hit by those shockwaves. It sits exactly 90 degrees straight up from the focus, taking the absolute shortest path to the surface.
Which, of course, naturally leads us to a pretty crucial question. How exactly does all that violent, pent-up subterranean energy manage to travel through literal miles of solid rock just to shatter a city up on the surface? I mean, it doesn't just teleport, right? It has to physically move. And that brings us to part 2, the race of seismic waves. Let's track how this energy actually moves.
So, picture this as a super high-stakes underground race. The absolute, undisputed winners, the P waves, or primary waves. These things are flying at a blistering 6 to 13 kilometers per second. They move by pushing and pulling the rock, kind of like a giant stretched-out slinky. A great way to anchor this is P for prime, meaning they are always the first to arrive at any seismograph. Plus, they're virtually unstoppable. They'll blast effortlessly through solids, liquids, and gases, the whole shebang.
Coming in second, we've got the S waves, or secondary waves. They're a bit slower, cruising at about 4 to 7 kilometers per second. Instead of pushing and pulling, they ripple through the earth like a violently shaken rope, moving everything up and down. But, and this is huge, they have a fatal flaw. Remember, S for solid? S waves can literally only travel through solid rock. The very second they hit liquid, poof, they completely disappear.
Okay, but here's the real kicker. When those internal waves finally slam into the surface, they spawn L waves, also known as surface waves. Now there's a mnemonic trick here, Dratal per love ka vinash, which basically means these love waves bring total destruction to the surface. And don't let the nice name fool you. They are the slowest waves, but because they're trapped entirely in a two-dimensional surface plane, they don't lose energy by spreading out in 3D. They just roll the ground like a massive carpet, tearing up foundations and causing the absolute maximum amount of destruction.
All right, on to part 3, the mystery of shadow zones. Time to play geological detective. So whenever a massive earthquake strikes, seismographs all over the globe light up, right? But scientists started noticing something super weird, a massive shadow zone. It's this huge dead band between 104 degrees and 145 degrees away from the epicenter. Inside that specific global band, the machines are completely eerily silent. Zero direct seismic waves reach there. It's honestly fascinating. It acts almost like a natural X-ray, highlighting some kind of massive obstruction deep, deep inside the Earth. And this is where the sheer genius of a scientist named Richard Oldham comes into play, back in 1906. He connected the dots. He realized, wait a minute, S-waves can't swim, right? They can't travel through liquid. So their sudden and total disappearance beyond 104 degrees basically proved that the center of the Earth couldn't just be solid rock. Without ever having to dig a single hole, Oldham proved that the Earth's outer core is actually this vast, churning ocean of liquid metal. How cool is that? Let's pivot to part 4,
the measurement of earthquakes. Let's get into the math and science of it.
Now, we really need to clarify how we actually measure all this destruction, mostly because you see the media get this wrong almost every single day. Let's make sure we never mix these two up again. Think magnitude equals Richter. The Richter scale measures the quantitative, sheer, absolute energy released way down at the focus. On the flip side, intensity equals Mercalli. The Mercalli scale is a qualitative rating from 1 to 12 that measures the actual physical damage and human impact. So if a massive quake hits a totally empty desert, it'll have a huge Richter magnitude but a very low Mercalli intensity because, well, there were no buildings around to fall down.
If you only take one mathematical fact away from this explainer today, let it be the number 32. Remember the trick. 10 ka tar, batis ka bahar. The Richter scale is logarithmic, meaning a jump from a magnitude 5 to a magnitude 6 means the physical wave height increases by 10 times. But the actual explosive energy released, that leaps by a staggering 32 times. It's not just a tiny step up, it is an absolute rocket launch of destructive power. Finally, we arrive at part 5, plate tectonics and tsunamis. Let's look at the global arenas for all this havoc.
Let's zoom out to the macro level for a second to see where these giant tectonic bumper cars are actually colliding. The reality is pretty stark. A whopping 63% of all quakes hit the Circum-Pacific Belt, what we ominously but accurately call the Ring of Fire. That's where the massive Pacific Plate is violently subducting beneath its neighbors. Meanwhile, another 21% strike the mid-continental belt. And this is highly relevant for us, because the Indian Plate constantly shoving northward into the Eurasian Plate keeps the rising Himalayas, and honestly all of North India, in a permanent high-risk earthquake zone.
But, it's not always just natural plate collisions causing all this. Human actions play a part too. For instance, trapping millions of tons of water weight at the Koyna Dam back in 1967 actually acted as a lubricant in deep rock faults, triggering a huge quake, something we call reservoir-induced seismicity. There's also isostatic adjustment, where the constant erosion of massive mountains like the Himalayas acts almost like a seesaw, forcing the Earth's crust to physically shift to balance the weight. But hey, nature does actually give us a heads up. Right before rocks finally snap, they form these tiny micro cracks that release trapped radon gas. So a sudden, sharp spike in radon, that's a literal direct warning that an earthquake is imminent.
Now, what happens when these massive elastic rebounds occur underwater? Well, the results are just catastrophic. The ocean floor violently snaps, acting like a giant subterranean punch that shoves the entire column of ocean water straight upward at the speed of a jet airliner. Out in the deep ocean, it barely looks like a tiny ripple, but as that wave hits the shallow coastline, something called wave shoaling happens. The friction drastically slows the front of the wave down, forcing all that fast-moving water behind it to pile up, creating a towering 100-foot wall of water. That is a tsunami, which is actually a Japanese word literally meaning harbor wave because it completely bypasses ships out at sea, only to absolutely annihilate coastal harbors.
As we wrap up this explainer, I want you to consider a pretty provocative thought. While we absolutely, rightfully fear their destruction, over the really long arc of geological time, earthquakes are actually a massive creative force. They sink coastlines to create deep natural harbors, they trigger landslides that form beautiful new lakes, and they push vital, deep earth minerals right up to the surface for us to use. So, are these violent tremors simply destructive forces, or are they literally the essential, vibrating heartbeat of a dynamic and living planet? I'm going to leave you to ponder that one. Thanks so much for joining me today, and I'll catch you next time.